Good evening, Lamai. Today we are going to discuss about the methods we use to describe the composition of a mixture. Right? So if you have to take mixtures, right, they will be with various chemicals, no? Right? So we are going to discuss today is actually how to represent the composition of a given substance or given chemical in a mixture, right? In this case, we are going to first study about the concentration, the term concentration. Let's discuss about that thing. Yes, our first study is about concentration. Right? First of all, what this means, what this concentration means. Concentration is actually the number of moles of a constituent substance, number of moles of a constituent substance in a 1 liter, or one may say 1 decimeter cubes of solution. This is the definition, right? Actually, concentration means if you are with a 1 liter solution, if you are with a 1 liter of solution, right, number of moles of constituent substance. Let's say you have the chemical A there, right? It is with some X amount of moles. So concentration of A is actually X moles per centimeter cube. In 1 liter of solution, you are with X moles. So the concentration of A is just X, right? So how to write this thing? Let's take the number of moles as N. It is better to come up with no number of moles of A as Na, right? So we can write the concentration of A can be expressed as number of moles of A divided by, right, the volume of the solution, That is how we represent the concentration. So moles will be calculated in moles. The unit is moles. For the volume, we have to come up with decimeter cubes, right? So the concentration means number of moles of the constituent substance in 1 decimeter cubes of solution, right? So what is going to be its unit then? Its unit is mole per decimeter cube, dm minus 3 per decimeter cube. Mole over decimeter cube means when decimeter cubes comes to the top, it is mole per decimeter cube, right? That is your unit for the concentration, right? So this is the equation we can use, right, for the concentration, right? So you can write here as well the unit is mole dm minus 3. So what you need to do to calculate the concentration is, first you need to come up with the number of moles of the constituent substance, then you have to divide that number of moles of the constituent substance by the volume in decimeter cubes of the solution, right? That is what we need to do, right, to come up with the concentration of a constituent substance. So concentration means the number of moles in a unit decimeter cube, no, right? In a unit liter, no, right? So we have to always express the volume in liters or in decimeter cubes, right? So That is the idea. So let's come up with some unit conversions here. So most of the times, the volumes will be given in milliliters or centimeter cubes, right? So let's discuss how to convert the centimeter cubes values or the milliliter values to decimeter cubes, right? Okay, let's do that conversion. Right, milliliters or the centimeter cubes. Centimeter cubes means actually milliliters, right? And the liters, the decimeter cubes values. Decimeter cube means liters. Right? So we have this kind of a conversion, right? We have this kind of conversion. It's very important, right? So if you are with x moles, sorry, x of cubic centimeters, x of cubic centimeters, that is equal to x into 10 to power minus 3 decimeter cubes. This is the most important unit conversion you will come across, right? These questions regarding concentration, right? You should know that, right? This is the unit conversion, right? So x milliliters means x into 10 to the power minus 3 decimeter cubes, right? So it is not hard to derive this stuff, right? So if you need a derivation, right? If you need a derivation, I'll write like this, right? If you need a derivation of this stuff, it's like this, no? So 1 centimeter cube, 1 centimeter means 10 to the power minus 1, 10 to the power minus 1 decimeters, right? So decimeter cube means, sorry, centimeter cubes means 1 centimeter into 1 centimeter into 1 centimeter. That will give you the centimeter cubes, no? So for that, we have to write it as 10 to the power minus 1 decimeters into 10 to the power minus 1 decimeters into 10 to the power minus 1 decimeter. So this will give you 1 centimeter cube is equal to 10 to the power minus 3 decimeter cubes, right? If you are referring to x amount of centimeter cubes, that means x into 1 centimeter cubes, that is going to be x into, right, x into 10 to the power minus 3 decimeter cubes. That is how you are supposed to derive the stuff, right? No need of a derivation. Just what you need to know is this simple unit conversion. X centimeter cubes means x into 10 to the power minus 3 decimeter cubes, right? This will be very helpful, right, when doing this kind of questions relating concentration, right? Let's come up with an example. Let's do some little example here, right? Okay. Let's do this example. So there's example appearing in your note at the page number 5, and it says, right, there's example, no? It says 250 milliliter cubes, so 250 centimeter cubes, so 250 milliliters of a solution contains 0.1 mole of NaOH. That was the question, right? So it says 0.1 mole of NaOH is there at 250 cubic centimeters of solution, right? So we are supposed to come up with the concentration of NaOH in this solution. Concentration of NaOH in this solution. So for the concentration, what we need to do is, actually we need to right? We need to divide the mole value from dm minus 3 value, right? We need to divide the mole value from dm3 value. That is how we are supposed to come up with the concentration. Just divide the mole value from dm cube value, right? Okay. So for that, first of all, we need to convert this centimeter cubes value to the decimeter cubes value, right? So 250 centimeter cubes means 250 into 10 to the power minus 3 decimeter cubes, right? No? 250 centimeter cubes means 250 into 10 to the power minus 3 decimeter cubes. You remember the unit conversion? X centimeter cubes means x into 10 to the power minus 3 decimeter cubes. That 250 centimeter cubes means 250 into 10 to the power minus 3 decimeter cubes, right? So now we can come up with the concentration of this NaOH, right? So we can write the concentration of NaOH concentration of NaOH as the moles value of NaOH should be divided by the dm3 value of NaOH, the dm3 value of the solution actually, right? So that is 250 into 10 to the power minus 3 dm cubes. So we can simplify this stuff, right? It's going to be 0.1 into 250 10 to the power minus 3. When it comes up, it is going to be 1000. So this will cancel off, right? So it will give you 0.4 moles per centimeter cube, right? Now, so that is a very simple calculation with the use of concentration. Now, normally this concentration of NaOH can be represented as like this. This square bracket also can be used to represent the concentration. This square bracket means this is the concentration of NaOH. Concentration of NaOH, right? So that can be written like that as well. So this is a very simple calculation to get that idea of concentration, right? Simply the concentration of a substance means number of moles in a 1 liter of solution. So here 250 milliliters contains 0.1 moles. That means 1 liter it contains 4 times of that. Simple as that. That is what you got from the calculation, right? Now, okay, let's discuss about another example. Let's come up with a very easy example, right? See, this is the example 2 appearing in your notebook, right? So at the page number 5, you have this kind of a question, right? So you are with a solution containing calcium carbonate, right? So there you have 300 grams of calcium carbonate and 5 decimeter cubes of solution. In a 5 decimeter cubes of solution, you have 300 grams of calcium carbonate. Now you are supposed to come up with the concentration of calcium carbonate. So they have asked you to come up with the concentration of calcium carbonate, right? Let's see how to do this kind of calculation. So again, the concentration means you have to divide the mole value. You have to divide the mole value of the constituent substance by the decimeter cube value of solution. You have to divide the mole value of the constituent substance with the decimeter cube value of solution. So decimeter cube values of solution is given, but first of all you need to convert this grams value into a mole value, right? Into a mole value. If you can do this conversion, then what you need to do is just divide this value from here. That will give you the mole dm minus 3 value, which is the concentration, right? Okay, let's do the stuff now. So to convert the mass, the G value to mole value, you may need the help of the G mole minus 1 value, right? So we know with each and every chemical formula, with each and every chemical formula, there is a hidden data, which is the G mole minus 1 value, which is the G mole minus 1 value, right? So let's hope they have provided these values, the atomic weights. Calcium is 40, right? The carbon is 12, and the oxygen is 16. So first of all, let's calculate the G mole minus 1 value of calcium carbonate, which is going to be very helpful to come up with the mole value of that, right? So the G mole value of calcium carbonate. So molar weight of calcium carbonate is actually equal to, you have the calcium, 1 of calcium, so 40 plus 1 of carbon, 12 plus 3 of oxygen, so 16 into 3, right? This gives you the G mole minus 1 value of calcium carbonate. So adding these things, right, will give you 100. So 100 G mole minus 1 is the molecular weight of calcium carbonate. So now we can use this G mole minus 1 value and G value to come up with the mole value of calcium carbonate, right? So let's come up with that. So calcium carbonate moles is equal to, what we need to do? So we have the G mole minus 1 value, we have the G value. So you need to cancel off the G value, right? So that it should be a division, right? It's like this number. So you have it some G value and a G mole minus 1 value. You have with a G value and a G mole minus 1 value. So with the use of these two things, you are supposed to come up with a mole value. That is our ultimate requirement now. So what we need to do? So we have to cancel off the G value. So surely a division should be done, and the mole thing should come to top, so that there should be a division like this. If you divide the G value from G mole minus 1 value, G's will cancel off and mole will come to the top to give you the, right, to give you the moles, right? So let's divide the G value, the 300 grams, from the G mole minus 1 value, right? So that will give you the number as 3 moles. So we are done with the number of moles of calcium carbonate, the interested substance. So now we can come up with the concentration of calcium carbonate. Concentration means the mole dm minus 3 value, so that we need to divide the mole value. We need to divide the mole value from what? We need to divide the mole value from dm3 value, right? If we are to divide the mole value from dm3 value, then you get the mole dm minus 3. That is the concentration. So mole value is 3. The dm3 value is given as 5 liters of the solution, right? So this will give you the concentration of the calcium carbonate in that solution. So 3 over 5 means 6 over 10, that is 0.6 moles per cube, right? Now, so that is going to be the concentration of calcium carbonate in this solution, right? Okay, done now. Right, let's do some questions, right? These are all about the introduction of concentration to you, right? Let's do some questions here regarding the concentration stuff, right? Okay, so there are a few questions available at the page number 6 in your note. Let's do the first one. Let's do the question number 1. This is the question. 100 milliliters solution of solution contains 2.02 grams of KNO3, right? So it's like this. So you have a solution. So actually 100 milliliters of the solution. That guy contains some KNO3. The amount is 2.02 grams, right? They are asking you the concentration of KNO3 in this solution. The concentration of KNO3 in this solution, right? So what we need to do? Concentration means the moles value should be divided by the dm3 value. So first, let's convert the gram value of the KNO3 to moles value. Actually, that can be done with the use of G mole minus 1 value of KNO3. With each and every chemical formula, there is that data, the G mole minus 1 value. So, and this is also needed to convert into decimeter cubes. So, we can simply do that thing in here as well. That is going to be 100 into the power minus 3 decimeter cubes. It's very easy, no? So, centimeter cubes can be converted like very easy, like this, no? X milliliters is equal to x into 10 minus 3 decimeter cubes, right? No? Milliliters and the centimeter cubes both are same, right? Milliliters and the centimeter cubes both are same. The liters and decimeter cubes both are same, right? Okay. Right. Let's do the stuff. So first of all, we need to come up with the G mole minus 1 value of the KNO3 to convert the G value to the moles, right? So molecular weight of KNO3. So you have 1 K, that is 39, and nitrogen is 14, and 3 of oxygens. So 16 into 3. So that will give you some value. Here is 48, 62, and 39. That is 101 G mole minus 1. That is the molar weight of KNO3. Now we can use this one to come up with the moles value of KNO3, right? So KNO3 moles will be equal to, right? You need to divide the G value from the G mole minus 1 value, right? Then the G's will cancel off and moles come to the top to give you the mole value, right? So the G value is 2.02, the grams value is 2.02, and the G mole minus 1 value is 101, right? That will give you, right? That will give you 0.02 as the number of moles, right? Then we can simply come up with the concentration of KNO3. Concentration of KNO3. So the concentration is then equal to 0.02 moles. The moles value should be divided by dm3 value. Moles value should be divided by dm3 value to come up with the mole dm minus 3. That's the concentration. So the dm3 value is this, right? So it is 100 into 10 to the power minus 3. So that will give you what? Right? This 10 to the minus 3 come to the top as 1000. So this is going to be 1, 2, 3. The 20 over 100 is actually 0.2. So that is the concentration of KNO3 in the solution, right? Okay. Let's do the problem number 3. Let's do the problem number 3, right? Here, you clearly see you have a solution, actually 250 milliliters of solution, and that contains some aluminium sulfate, right? It is a aluminium sulfate, right? So what is the amount? It is 34.2 grams, right? They are asking you the concentration of Al3 plus as well as the concentration of sulfate ions, right? So with the use of this, first you need to come up with the moles of these two guys. Then you can come up with the concentration by using the dm3 value. So this can be easily converted to dm3, right? And this thing should be converted to the moles of aluminium and the sulfate ions. That is what they are asking, right? Okay, let's do the stuff. So first, as the number grams of aluminum sulfate is given with the use of G mole minus 1 value of this stuff, we can come up with the moles of aluminum sulfate, right? Then we can use the these ratios, stoichiometric values, to come up with the moles of the Al3 plus as well as the sulfate ions. Let's do the stuff, right? So it's like this. So first come up with the molar weight of aluminum sulfate, right? That is actually, you have 27 2, that is 54, plus this is actually 32, 64 and 96 into 3, right? Such kind of stuff, right? So it is going it will give you 96 into 3 is actually 288, all right, and 54, that is 342, right? It's 342. So G mole minus 1, right? So that we can come up with the moles of aluminum sulfate. That is 44. Sorry, that is the G value should be divided by the G mole minus 1 value. G value is 342, sorry for that, 34.2 grams divided by 342. So the moles value will be given as 0.1, right? Now, as we know, the aluminum sulfate is actually equal to 2 of Al3 plus ions and 3 of SO4 2 minus ions, right? So as we know the number of moles of aluminum sulfate as 0.1 moles, we can say number of moles of aluminum 3 plus is 0.2 and the number of moles of SO4 2 minus is 0.3. So this thing should be done, Laman, right? This is the given data, this is the known data. So we need to come up with these ones. So these are the required data. So first you need to build up a relationship between the known data and the required data. That is what we have done here. At the first lesson we had discussed about that, right? If we know some data about some species and if we are supposed to come up with some data of another species, first we need to build up a relationship between the known data and the required species, right? So the known data is about the aluminum sulfate. First we need to build up a relationship between the aluminum sulfate and the required Al3 plus there. So that is the relationship, right? One aluminum sulfate contains 2 Al3 plus ions, 2 of Al3 plus ions, 2 of Al3 plus ions, and 3 of sulfate ions. 3 of sulfate ions, right? So that as the stoichiometry is 1 to 2 to 3, you can come up with 0.2 moles here and 0.3 moles here, right? Then as we know the number of moles, we can use these values. As we know the number of moles of aluminum 3 plus as well as sulfate, we can use these values to come up with the mole dm minus 3 values, right? So with use of this, right, volume is given now. So let's come up with the concentration of the aluminum 3 plus here. So the concentration of aluminum 3 plus, right, can be written as the moles value of aluminum 3 plus 0.2 should be divided by dm3 value of the solution. So dm3 value is actually 250 into 10 to the power minus 3 dm3. So x milliliters is equal to x into 10 to the power minus 3 deciliters, right? That is the idea. So this 10 to the power 3 comes to up, right, at top, right, as 1000 1000 will be divided by 250. So that will give you 4. So 4 into 0.2, that is 0.8. Right now, let's do the same stuff for the sulfate as well. The concentration of sulfate is actually equal to moles of sulfate, the mole value, that should be divided by the DM3 value. The DM3 value is the same, right? Both are in the same solution, same volume, right? So 250 into 10 to the power minus 3 DM3. That will give you the number as 1.2 moles per cube. So those are the two concentrations of the two respective ions of aluminum sulfate. Right now, just do the calculation. Right, then let's do the question number 2 appearing at the page number 6. No, yeah, in page number 6. Let's do the question number 2. Let's do the question number 2 appearing in page number 6, right? Okay, see, this is the question, right? They have given you this equation, right? And they have asked you to find the amount of moles of aluminum hydroxide needed, right? Amount of aluminum hydroxide needed to react with 0.2 molar 50 cubic centimeters of H2SO4, right? So what we need to do here? So basically, they have given some data about the H2SO4. They have given some data about the H2SO4, and they are asking us the moles of aluminum hydroxide. They are asking us the moles of aluminum hydroxide. So what we need to do? So basically, these are two species available appearing, right? So they have given some data of the H2SO4 and they are asking some data about the aluminum hydroxide. So what we need to do? First of all, we need to convert the given data of the given species to its number of moles, right? Then we can use the 3 to 2 mole ratio to come up with the number of moles of the required species, right? That will give you the ultimate result here, because as they are asking the number of moles of aluminum hydroxide, right? Again, I'm telling you what we need to do. The data are given for the H2SO4. They are asking some other data about the aluminum hydroxide. So what we need to do is, actually first we need to convert the data of the H2SO4 to its number of moles, right? We can use the volume data and the mole DM-3 data, the concentration and the volume data, to come up with the number of moles of H2SO4. First we need to come up with that. Then we can use this molar ratio, the 3 to 2, to come up with the number of moles of aluminum hydroxide. That is what is required, right? That is how we are supposed to solve this question, right? Let's do the stuff, right? So first let's come up with the number of moles of H2SO4, right? So H2SO4 moles, right? So to come up with the moles, right? Actually, they have provided the mole DM minus 3 value. So mole DM minus 3 value and the DM3 value. This can be converted to DM3 value. No? So these two values are given, and they are supposed to. They have asked you to come up with some mole value. So what we need to do? Right? You need to come up with some mole value. So mole value should be there, right? And these two should be cancelled off. To cancel off these two guys, as this is a minus 3, right? Actually, we need to multiply this stuff. If you multiply this with this, the DM minus 3 and the DM3 will cancel off. So that is what we supposed to do to come up with the mole value of the H2SO4. So let's do the stuff. So let's multiply the 0.2, the mole DM minus 3 value, with the DM3 value. 50 cubic centimeters means 50 into 10 to the power minus 3 decimeter cubes. So these decimeter things will cancel off, and the number comes in terms of moles. So 50 into 0.2 is actually 10, that 10 to the power minus 3, that is the number of moles of H2SO4, right? Then we could say, right, we could come up with the number of moles of aluminium hydroxide, that is the bonded thing, that is the bonded, right? So we can write like this as aluminium hydroxide 2 H2SO4 is actually 2 to 3 ratio. We can write using stoichiometry the moles of aluminium hydroxide. So 10 into 10 to the power minus 3, that number of moles is actually representing 3 portions. This amount of moles is actually representing 3 portions. The H2SO4 aluminum, it is actually representing 3 portions. But we need such 2 portions. So what we need to do? First, the H2SO4's value, as it is representing 3 portions, first divide it with 3. So that will give you the value for 1 portion. That will give you the value for 1 portion. So we need such 2 portions. So multiply with 2. That is how we are supposed to come up with the aluminum hydroxide moles. So that value will be given as 20 over 3 is 6.66 into 10 to the power minus 3. That is the number of moles of aluminum hydroxide needed to completely react with this amount of moles of H2SO4 or this volume of H2SO4. Right now? So that is how we are supposed to solve this question. Right? Right. Let's do the Roman number 2. Right here. Question number 2, Roman 2. See, in this case, right, what they are asking? They are asking find the volume of 0.1 mole H2SO4. So volume of 0.1 mole H2SO4. That is what they are asking. It's what they are asking. This is the asking data. The asking data is about H2SO4. The given data is about aluminium hydroxide. Given data is about aluminium hydroxide. Asking data is about H2SO4, right? So it is again the relation between the H2SO4 and the aluminium hydroxide, right now? Right. So what we need to do then? So first of all, we need to come up with, is the given, no? The given, no? The given. Is the asking. So first of all, we need to come up with moles of the given species, right? So the grams of aluminum hydroxide, first we need to convert that into the moles of aluminum hydroxide. So that can be done with the use of G mole minus 1 value of aluminum hydroxide, right? Okay. So after coming up with the number of moles of aluminum hydroxide, we can use this 2 to 3 ratio, the mole ratio, to come up with the moles of H2SO4, to come up with the moles of H2SO4, right? So that will ultimately leads you to come up with the required data, the volume of H2SO4 as the concentration is given. So always the bridge between the given species and the asking species is also always provided by the mole ratio. So it's a mole ratio. So first of all, you need to come up with the moles of the given species to continue the calculation, right? So that is the idea. So let's do the proceedings, right? So first of all, you need to come up with the moles of aluminum hydroxide, right? So to come up with the moles of aluminum hydroxide, actually to convert the grams to moles of the aluminum hydroxide, first you need to use the G mole minus 1 data of the aluminum hydroxide. Let's calculate that, right? So G mole minus 1 data, right? So 1 aluminum is there, that is 27, plus we say 16 and plus 1, 17, 17 to 3. So it is 51 and altogether 58. Sorry, I'll write it here. Is 58 G mole minus 1, right? So that we can come up with the moles of aluminum hydroxide. So basically the G value should be divided by the G mole minus 1 value, right? So if you divide the G value from the G mole minus 1 value, then the G's will cancel off and you will get the number in terms of moles, right? So that is the idea here. So 15.6 G value should be divided by the G mole minus 1 value, right? So that is 0.1. Sorry, what we have calculated is, sorry, it is 78, no, sorry, 70. So that will give you a value as 0. Right, 2, no, 0.2. That is the number of moles of aluminum hydroxide. So that that number of moles of aluminum hydroxide can be used to come up with the number of moles of H2SO4. So H2SO4 moles so 0.2 moles is actually for 0.2 moles is actually for 2 portions. We need such 3 portions for the H2SO4, right? 0.2 is actually the number of moles of aluminum hydroxide. That is representing 2 portions, right? So for 1 portion, this value should be divided by 2. So this will give you, for 1 portion, we need such 3 portions, right? We need such 3 portions, right? So that will give you the H2SO4's value, right? So that is going to be what? This will be divided, right? So it is going to be 0.3 moles. So as we know the number of moles, and as we know the concentration, the mole value and the mole dm minus 3 value is known. Those values are known. So we need to come up with some dm3 value. The volume can be represented in dm3 value. So let's try to come up with that thing, right? So H2SO4 volume. So what can we do? So we can, right, use the mole dm minus 3 value and the mole value to come up with DMQs, right? That is what we need, right? So for that, you need to cancel off the mole value. We need to cancel off the mole value to come up with the DN3 value, right? So definitely a division should be done then. Definitely division should be done to cancel off the mole value. And to come up with the value with DN3, so you need to divide this thing with this, right? That is the idea. If you divide this thing with this, the moles value will cancel off and DN3 comes to top as D minus 3 will come to top as DN3, right? That is the idea, right? So let's do the stuff. So the volume, for the volume, what we are supposed to do is just divide the mole value from mole dm minus 3 value. So mole will cancel off and dm minus 3 comes to top as dm3. That represents the volume, right? So the mole value is 0.3. Mole dm minus 3 value is 0.1. So the final answer is going to be what? Yes, 3 decimeter cubes, right? Or one can say, yeah, that is the idea, right? That is enough, no? Just in decimeter cubes, you can take the answer, right? One can write it as 3000 centimeter cubes. This is okay, right? 3 decimeter cubes, right? No, that is all about the second question, Roman number 2, right? Of your second question. Right. Let's do the question number 3, right? Roman number 3 actually of your question number 2 appearing on the page number 6, right? Okay, let's do. So first copy the answer for the part A. Answer the part A. See what we can write here. So calculate the aluminum hydroxide mass needed. That is the question, right? That's the question. So actually given data is about aluminum sulfide and they are asking for aluminum hydroxide. Asking data is about aluminum hydroxide, right? So let's see. So first of all, what we need to do? First of all, what we should convert the given data into its number of moles. So we need to convert the aluminum sulfate 171 grams into number of moles of aluminum sulfate, right? Then we can use that number of moles of aluminum sulfate to come up with the moles of aluminum hydroxide using the 1 to 2 ratio, right? Then we can come up with the mass of aluminum hydroxide using its G mole minus 1 value. That is how we are supposed to solve this question. Let's do the stuff, right? So given is for aluminum sulfate. So first come up with the number of moles of aluminum sulfate, right? To that its molar weight is needed, right? So molar weight of aluminum sulfate, that is equal to 2 of aluminium, so 27 into 2, plus the sulfate into 3, right? So sulfate, this is the 2, 16 into 4 is 64, altogether 96, 96 into 3, 96 into 3. So that will be given as this is 288, and this is 54, no? 342, no? This is 342. So with the use of G mole minus 1 value and the grams value of aluminum sulfate, we can copy the moles of aluminum sulfate, right? So it's going to be 3. Sorry, the value is 171. No? The G value should be divided by G mole minus 1 value, right? Come up with in terms of moles, right? So the G value is 171. G mole minus 1 value is 342. So this will be given as, this will give us 0.5 moles. The half, no? Right? The half value, right? So 0.15 moles of Al2SO4 thrice is there. So then we need to come up with the AlOH3, that is the asking data, number of moles of the number of moles of that thing. So aluminum hydroxide moles. So 0.5 of aluminium sulfate, 0.5 of aluminum sulfate is actually representing one portion. So representing one portion. So we need such two portions. We need such two portions, right? So the value is just 1 mole. Then we can come up with the mass of, right, aluminium hydroxide, right? So mass of aluminum hydroxide. So that can be solved by multiplying the G mole minus 1 value with the moles value of the aluminum hydroxide, right? So multiply the moles value from G mole minus 1 value. So that thing will cancel off the most things to come up with G, right? So what is the G mole minus 1 value of aluminum hydroxide? Just do some calculation here. So aluminum for the aluminum hydroxide. So aluminum is 27. So OH, the oxygen is 16, hydrogen is 1, 17. 17 into 3 is 17 into 3 is 51. So that is 78 altogether. So the aluminum hydroxide G mole minus 1 value is 78. Right? So multiply by 78, right? So that thing will give you 78 grams. That is the answer, right? No? Okay. So that is about the mass of aluminum sulfate. That is the part A of the Roman number 3 question. Right? No? Okay. Let's do the part B. part B as well. Right. Let's do the part B. Right. So ask in data. Calculate the concentration needed of 500 cubic centimeters H2SO4. This is the asking thing. The asking chemical H2SO4. And the given thing is this one. It's the given data. They have given some data about the aluminum sulfate and they are asking about H2SO4. Right. So first of all, the given thing should be converted to its number of moles. Right. Given thing should be converted to its number of moles. Right. So with the with the part A, we have done that thing. Number of moles of aluminum sulfate we had calculated. Right. That was given as 0.5 moles, right? So that moles can be now converted to the H2SO4 moles, right? H2SO4 moles, right? So number of moles of aluminum sulfate is found, right? Then that thing should be converted to the moles of H2SO4, right? So that can be done with the use of 1 to 3 ratio, right? So moles of H2SO4 is actually given by 0.5 moles actually representing one portion. So divided by 1, right? Give you one portion, and we need such 3 portions, right? The value is going to be 1.5 moles. That is the number of moles of H2SO4. Now we need to combine the mole value and the CM3 value, which is actually the DM3 value. We can convert the CM3 to DM3 to come up with mole DM minus 3 value. To come up with mole DM minus 3 value, right? Okay, let's do the stuff, right? So the concentration of H2SO4 is actually what we need to do is we need to divide the mole value by the DM3 value. That will give you the mole DM minus 3 value, which is the concentration, right? So the mole value of H2SO4 is 1.5, right? And then the volume of H2SO4 is what? Volume of H2SO4 is 500 cubic centimeters. So in decimeter cubes, 500 into 10 to the power minus 3, no? Right? So this 10 to the power minus 3 comes to top as 1000. So 1000 will be divided by the 500 to give it as 2. So 2 into 1.5 is 3, no? This is how we are supposed to solve for the part B of the Roman number 3, right? Let's complete the stuff. Right. Let's discuss about another very important type of calculation regarding concentration. Right. Normally, Lamai, in concentrated HCl bottles, in concentrated HCl or HNO3 kind of concentrated acid bottles, right? They will give you the composition, right? Not normally in the straightforward manner as concentration, but normally they will give you the composition in terms of density and the weight percentages, right? So density of the solution as well as the weight percentage of the corresponding substance will be given into the substance. So the solute is given, and that is how normally the composition will be represented. Normally in concentrated H2SO4 bottles, concentrated HCl bottles, as well as concentrated nitric bottles. Normally in concentrated acidic bottles, acid bottles. That is the way of representing the composition. So let's try to convert those numbers into the mole dm minus 3 or into the concentration, right? If the composition is represented with the mass fractions or the mass percentages and the densities of solution, let's try to convert those values to the concentration of the solute there, right? Let's try to do such a calculation, right? So the topic is that, right? So finding out the concentration of the substance in a solution when the mass percentage and the density are given. When the mass percentage and the density are given. This is such a situation, right? So the concentration HCl bottle is given and its weight percentage is given as 66.5 and the density is given as 1.12 grams per centimeter cube. Grams per centimeter cube, right? Per centimeter, sorry for that, right? So the weight percentage, what this means? The weight percentage means in 1000, in 100 percentage, no, in 100, right, grams of the solution, how many grams of HCl are there? That is the weight percentage. In 100 parts of the total solution, how many parts of constituent substance is there? That is what is meant by the weight percentage. If you are take it as grams, in 100 grams of the solution, how many grams of HCl is there? That is what is meant by weight percentage, right? The density of the solution means that is actually the mass in grams of 1 cubic centimeter. Mass in grams of 1 cubic centimeter, right, of the solution, right? So 1 cubic centimeter of solution, weight 1.12 grams. That is what this means, right? So that is all about the density, and the density and the mass percentage are given for the concentration HCl, and they are asking the concentration in mole dm minus 3 terms, right? So let's try to solve this one, right? For this kind of a calculation, right, we actually use the definition of the concentration. What is the definition of concentration? Definition is number of moles of the constituent substance in 1 liter or 1000 centimeter cubes of the solution. That is the definition. So the concentration of HCl means, so one can say the concentration of HCl means concentration of HCl means that is the number of moles of HCl in 1 decimeter cube. 1 decimeter cube, or one can say 1000 centimeter cubes of solution, right? This is the definition, right? This is the definition. Let's use this definition to copy the concentration of the HCl here, right? Okay, let's do the stuff. So our plan is this. First, we will take 1 decimeter cube or 1000 cubic centimeters of the solution. Let's take, right, 1 decimeter cube or 1000 centimeter cubes of the solution, right? Consider 1 decimeter cube or 1000 cubic centimeters of solution. Considering this, first we will calculate the mass of the solution. Mass of 1 cubic decimeter cube of solution. That can be done with the use of density, right? Okay, that is our first task here. So mass of solution can be found with the use of dV m is equal to dV, no? Mass of solution will be given by density of solution into volume of the solution. So density is given as 1.12 grams per centimeter cubes. So volume is actually 1000 cubic centimeters. So volume should be applied with cubic centimeters. Volume should be applied with the cubic centimeters. Then only the cm 3 terms will cancel off to give you the number in unit g, grams, right? That is what we require, no? So we have to cancel off the cm minus 3, no? So that you have to multiply with cm3 number, right? So the cm3 thing cancel off and giving you this number 1120 grams. This is the mass of solution. Then with the use of weight percentage, we can come up with the mass of the HCl. Right? Out of 100 grams of the solution, 36.5 grams belongs to HCl. That is what weight percentage means, right? So we can use that thing to come up with the mass of HCl, right? So mass of HCl is then if you take this right, if you take 100 grams, 36.5 is actually HCl, right? So as this one representing 100 portions, right? The HCl amount is 36.5, right? So that is the idea. No? This is total mass. No? Total mass is representing 100 portions. So such 36.5 portions are there with HCl, right? The use of weight percentage, right? So that is the number of grams of HCl, the mass, right? So now we can convert this grams of HCl to moles of HCl. That will be the concentration of HCl. Right? If you can convert this grams of HCl to moles of HCl, that will be the concentration, because the concentration means number of moles of HCl in 1 decimeter cubes of solution. We considered 1 decimeter cubes, right? Let's do the stuff. So I'll write it here. Right? So let's write it here as well, right? So that we can write the moles of HCl. The moles of HCl. This is the mass of HCl. G value. To copy the moles of HCl, we need to divide that thing with G mole minus 1 value. If you have to divide this thing with G mole minus 1 value, the G values will cancel off and give you the value in moles, right? So what is the G mole minus 1 value? For the HCl, hydrogen is 1, Cl is 35.5. So the G mole minus 1 value is 36.5. Right? So the 36.5 will cancel off easily. Right? Then we can divide this stuff. This is going to be 11.2. This value is going to be 11.2 moles. Right? So the moles of HCl in 1 cubic decimeters of the solution is 11.2. So that means your concentration is 11.2. Right? So that we can write. I'll write it here. So that HCl concentration is going to be 11.2 moles in what? 1 decimeter cube of solution. So your concentration is going to be 11.2 moles per decimeter cube. And that is how we are supposed to do this kind of calculation, right? Always do the calculation considering 1 decimeter cube of solution and try to come up with the number of moles of the contained substance there, and that will be your concentration. That will be your concentration. Right now, so that is how you're supposed to solve this one. Right now, okay, that is some question regarding the concentration and density of the solution as well as the weight percentage. Let's discuss about the concept of molality, our second method of expressing the composition of a mixture. Molality, right? First of all, what this means. Molality is actually the moles, number of moles of the solute in a 1 kilogram of the solvent. This is the definition. This is the definition of the molality, right? Number of moles of the solute in 1 kilogram of the solvent, right? So it's like this. See, you are with a solution. Solution means what? Solution means solute and the solvent, right? You are with a solution. That means solution means solute and the solvent, right? Let's say you had prepared a solution by adding the solvent and the solute, right? Say you have added the solvent H2O, right, and this is solvent, and you have added some A, this is some A solute, right? Okay, so and prepared a solution, right? A is there, and we can define A equals solution. This is the solution. Solute and the solvent are there, right? So we can write the molality of A. Mole is the solute, right? A is the solute now. So we can write, I'll write it in red color. Molality of A, the solute, can be written as, right, the moles of A divided by the kilograms of the solvent, right? As H2 is your solvent, right? We can write like that, right? So basically, molality is given in terms of moles per kilogram. So the unit of molality is moles per kilogram. You can write it there, right? Moles per kilogram is your unit there. So as a general expression, we can write, molality is moles of solute divided by mass of solvent. This is represented in kilograms, and this is in moles, right? So the unit here is moles per kilogram, right? No? That is a simple idea, right? Solutions are made by mixing the solvent and the solute, no? Right? So the molality of the solute is So the moles of that solute in your solution divided by the mass of solute in kilograms, right? So the unit is moles per kilogram, mole kg minus 1, right? Okay, let's do a simple example. Let's do a simple example to get this idea clearly, right? Say you have a sucrose solution, right? Where 1 kilogram of water is added to 1.25 moles of sucrose. Okay? You have prepared a sucrose solution. You had prepared a sucrose solution. See, you are with a sucrose solution. When analyzing that thing, right? When analyzing that thing, right? Let's say 1 kilogram, right? 1 kilogram of solvent, 1 kilogram of water, let's say 1 kilogram of water contains 1.25 moles of sucrose, right? So you have a sucrose solution where 1 kilogram of water contains 1.25 moles of sucrose. Let's try to come up with the molality of sucrose here. Molality of sucrose here. We can write the molality of sucrose. Molality of sucrose is actually what? Molality of sucrose is moles of sucrose. Moles of sucrose, that is 1.25 moles divided by kilograms of solvent. Kilograms of solvent. Solvent is H2O, so 1 kilogram. Kilograms of solvent. Moles of solute, which is sucrose, divided by kilograms of solvent. So mole of sucrose is going to be 1.25 moles per kilogram for this sucrose solution. Right? Let's complete the stuff appearing at the page number 7. The first example. Right now. So just copy the second example as well. Just copy the second example as well. See what it says, right? So at the second example, this kind of stuff is given. It is said that a solution is prepared by, this is the example number 2 appearing at page number 7. The solution is prepared by adding 5.8 grams of NaCl to 1 decimeter cube of pure water, right? And they are asking to find out the molality of NaCl in this solution. That is the question here. Some more data are provided, right? They have provided the molar weights or the atomic weights: sodium 23, Cl 35.5, and the density of water is also given. Density of water is given as 1 gram per centimeter cube. Right? This is your question. This is your question. Right? See what this looks like. So basically, what they have done is, first they had 1 liter of or 1 decimeter cube of H2O, pure water, or one can say H2O, was there, and they have added some NaCl. How many grams? 5.8 grams. This is your solvent, this is your solute. So what we need to do? First you need to come up with, right, moles of the solute. Moles of the solute. So this thing should be converted to moles. Moles of solute should be divided by kilograms of the solvent. So this value should be converted to kilograms. So if we can do these two things, these two conversions, we are done. So molarity is moles of the solute divided by kilograms of the solvent, divided by, right, this is mole kg minus 1. This is minus 1, not just the one, right? Minus 1, that means mole over kg, mole over kg. So moles of solute should be divided by kilograms of the solvent. So first, right, identify the goal like this. First identify the goal like that. What is the goal? I'm writing it again. Your goal is to find out the moles of the solute and the kilograms of the solvent. Right, like this, right? Molality of NaCl is actually moles of NaCl, moles of solute divided by kilograms of solvent. That means kilograms of H2O, right? This is our goal, right? So first identify the goal properly. Right? This is our goal. Right? So if you can solve for these two things, we can divide the stuff and come up with the answer. Right. So first thing is actually finding out the number of moles of NaCl. So mass is given. And we need to convert it to moles. So what we can do? So basically we need to come up with the G mole minus 1 value. So with the use of G mole minus 1 value with the G value, we can come up with the moles, right? So sodium moles is equal to its G value should be divided by the G mole minus 1 value. The G value is given as 5.8. Now just do some little bit of correction. It should be 5.85 now. It should be 5.85, right? I'm printing error. The additive, right? It should be 5.85, right? So the number of number of grams is 5.85. So G mole minus 1 value of the sodium. What is the G mole minus 1 value of sodium? Right? So it is not about sodium chloride, no? Sorry, sodium chloride. What is the G mole minus 1 value? Right? The sodium is 23, chlorine is 35.5. 23 and 35.5 will give you 58.5. Right? No? So the moles of NaCl is going to be then 0.1 mole. That is our first part, coming up with the number of moles of NaCl. Let's do the second part. Then we need to come up with the mass of the solvent. Finding out the mass of H2O, basically in kilograms, right? We need the value in kilograms. Substitute here. So mass of the H2O can be found with use of its density. So m is equal to dV, right? Okay. So H2O mass is, right, m is equal to dV. The density is 1 gram per centimeter cubes into V. The volume should be substituted in terms of centimeter cubes now, right? To get rid of centimeter cubes to come up with a G term, G unit, right? Because we are referring to mass now. So the mass unit should be there, right? So that you have to consider of the Cm minus 3. For that, you have to multiply the stuff with the Cm3. So 1 liter means, right? 1 liter, decimeter cubes means liter, right? 1 liter means 1000 milliliters, 1000 milliliters. So that means 1000 centimeter cubes. Milliliters and the centimeter cubes are the same, right? 1000 centimeter cubes. So mass of H2O is then what? 1000 grams. That means 1000 grams. That means 1 kilogram. 1 kilogram. Right? No? So moles have been calculated, and the mass of H2O is also calculated, so that we can compare the molality of NaCl. So that molality of NaCl is actually moles of NaCl should be divided by the mass of solvent in kilograms. That is what? That is 1 kilogram. So the final number is 0.1 moles per kilogram. Right now? So that is the molality of your NaCl solution. Right? That is how we are supposed to solve this kind of question. Right now? Let's complete this stuff. Right. Next, let's go toward the next topic. Right? That is actually the compositions given in fractions. Right? We had started with the concentration, then we moved to the molality of a solvent, sorry, of a solute in a solution, right? Now, the third thing we are going to discuss is actually the concept of composition given in fractions. Under that, we will start up with the mass percentage, mass fraction, mass percentage, and the ppm concentration, right? Let's discuss what these things mean, right? Okay. So the idea is this, right? The idea is this. Let's say you have some mass. Let's say you are with some mass, some sample. See, you are with some sample, right? You are with some sample, and let's say the mass of the sample is, right, m total mass of the sample, right? Then you have a, let's say you have a solute, sorry, you have a chemical here, A, chemical A, right? And let's say its mass is Ma. You have a chemical A in your sample, and some other stuff as well. Some other stuff as well, impurities, so some other stuff, right? So as A is there, and it is with a mass A, right? So the mass fraction means, mass fraction means, let's see, you can write it as mass fraction. Let's say mass fraction of A. Mass fraction of A means that is the mass of A, the mass of A divided by the total mass of sample. Total mass of the sample. So we can write it as the MA, mass of A, divided by total mass. MA or M total. This is the mass fraction. If you have to think of mass percentage, if you think of mass percentage of A, it is actually, right, number of mass units in 100 units of the 100 mass units of sample. That is the idea, right? So it can be simply represented here as mass of A divided by mass of sample into 100, right? Into 100, right? So, or else we can write it as MA or M total into 100, right? Simple as that. Mass percentage, right? Normally we denote the mass fraction, right, with this symbol W over W, weight percentage, sorry, weight fraction or mass fraction. Here the percentage will be represented as percentage W over W, weight percentage. Normally we use that symbols, those symbols to represent the mass fraction and the mass percentage. So actually mass fraction and mass percentage both are referred to as unitless quantities. Unitless quantities. So if you have to apply the mass of A in grams, you have to apply the mass of sample also in grams, right? So the grams will cancel off. So unitless quantities. Here as well, if you apply the mass of A in kilograms or something, kilograms or grams, so you have to apply the mass of sample in the same unit. So the units will cancel off, giving you a unitless, not unitless, just a number, right? Okay. So no units with the mass fraction as well as mass percentage, right? So you don't carry any units, right? These guys carry no units, right? Even for this one, no unit, right? Then we will come up with some new term referred to as ppm, right? Referred to as ppm. That is actually the mass fraction into million, right? This is a bit about that thing, right? After writing the equation, so ppm concentration, we can write the ppm concentration of A can be represented as mass of A divided by the mass of sample into million to the power 6, right? So in symbolized manner, the mass fraction is the MA over M total into million. That is referred to as the ppm concentration, right? So normally as a symbol like this, you just write the ppm, like the percentage sign. Here you will write the ppm, right? Again, it's a unitless quantity, right? Won't carry any unit. So if we are applying the mass of A in grams, the total mass also should be applied in grams. So the units will cancel off, right? So no unit here as well. Right? These are the first three things we are going to follow. mass fraction, mass percentage, and ppm concentration. Right? Okay. You can box the stuff. So these are there in the note, right? At the page number 8, you can clearly see these things are appearing. So if you have to think of a bit, if you have to discuss if we have to discuss a bit about the ppm concentration, and it's like mass fraction into million. It is also referred as parts per million. This ppm stands for parts per million. This stands for parts per million. It is why we multiply by 10 to the power 6, right? So here it is actually parts of the consuming substance per one part, like, right, grams of A, kilograms of A per 1 kilogram of sample, kilograms of A per 1 kilogram of sample. Here kilograms of A per 100 kilograms of sample, per 1 kilogram of sample for these things. So multiply by 100 per 100 kilograms of sample. In here, this will give you per 1 kilogram of sample into million means per million kilograms of sample. Kilograms of A in million kilograms of sample, parts per million, like that. If you are taking with kilograms, both are with kilograms. If you are thinking of grams, those are grams, right? So like that, parts per million means, right, number of the amount of parts of sensory substance in million parts of the sample. Percentage means parts of sensory substance in 100 parts of sample. Mass fraction means parts of sensory substance in one part of the sample, right? That is the idea here, right? Let's do some calculations and try to understand these things more clearly, right? Okay, so some example is given in your note. Let's go to that. Right, what is that example? It says at the example at the page number 8, it says 50 grams of sample contains 0.2 moles of calcium carbonate. So you have a sample, right? You have a sample. Example appearing at the page number 8, right? You have a sample, right? So actually 50 grams of sample, no? 50 grams of sample. They are saying that contains 0.2 moles of calcium carbonate. So you have calcium carbonate there, 0.2 moles, right? They are asking you to find out the mass fraction and the mass percentage of calcium carbonate. Mass fraction and mass percentage. Those are the two questions they are asking. Calculate the mass fraction and the mass percentage. Right? Let's do kind of a calculation. Right? To come up with the mass fraction as well as mass percentage, you should know the mass of the consuming substance and should know the mass of the sample. We have to divide those two to give come up with the mass fraction. If you need to come up with the mass percentage, what you need to do is just find the mass fraction as earlier and multiply that thing with 100. That will give you the mass percentage, right? Let's do the question then. So mass of sample is given, known. We are happy with that, but moles of the interested substance is given. So first of all, we need to convert this thing into mass. We need to convert this into mass. As this thing is given in grams, we need to convert this into grams. So with mass fractions and mass percentages, right, you are not with any units, so units should be cancelled off. So with the same unit as samples mass, you have to come up with the instead substance mass, right? Okay, let's first do that calculation, right? So first we need to come up with the mass of calcium carbonate to find out the mass fraction of the calcium carbonate, right? So calcium carbonate mass. Calcium carbonate mass. So for that, you need to combine the mole value with the G mole minus 1 value to come up with some G there, right? So the G mole minus 1 value, if you are to multiply that thing with moles value, then you will come up with some G value, because the mole minus 1 to mole will cancel off, right? Okay, what is the G mole minus 1 value of calcium carbonate, right? Let's calculate that thing. So for the calcium carbonate, calcium is 40, carbon is 12, T of oxygens means 48, so that is 100. G mole minus 1 value is 100. So 100 should be multiplied by 0.2. So the value is going to be then 20 grams. So calcium carbonate mass is known. So we know the mass of sample as well, right? Sample mass is known also. They have given that thing. That is 50 grams. So now can't we come up with the mass fraction then? The mass fraction, so one can write it as WOW for the calcium carbonate, right? What is that value? So the mass of calcium carbonate should be divided by the mass of sample. That is the mass fraction. So it will be 20 over 50 means 0.4. Right now? So what about the mass percentage? Mass percentage for the calcium carbonate. So what we need to do is then the mass of the instead substance calcium carbonate should be divided by the total mass of the sample, and we need to multiply it with 100. That is what percentage means, right? So that it is going to be 40%. Right? That is how we are supposed to copy the mass fraction as well as mass percentage. So no unit appearing with those numbers, right? Okay, right. Just complete the stuff. So this is actually the example at the page number 8, right? Just complete that. Let's try to do the first question appearing at the page number 8, right? There are 2 questions now at the page number 8. Let's do the first one. That is a question regarding the weight percentage, right? Let's see how to solve this kind of question. What it says, first of all, a sample contains an iron salt and an inert material, right? So you have sample, right? You have sample like this, right? It is the iron salt and an inert material, right? The Fe is in +2 oxygen state. So Fe is in +2 oxygen state here, there, right? This is some inert material. Fe is stuff and inert material. This is your sample, na? 2 grams of sample was dissolved in dill acid. So you are with 2 grams. right? So 2 grams of sample was dissolved in dill acid, and all the Fe2 plus were reacted using a 0.1 molar MnO4 minus, right? So you have reacted this thing with 0.1 molar MnO4 minus solution. MnO4 volume consumed was 20 cubic centimeters. So anyway, you have added here some MnO4 minus, right, with 0.1 molar concentration. These are the data available in the question, and 20 cubic centimeters was consumed, right? 0.1 molar MnO4 minus 20 cubic centimeters was consumed to totally react with the Fe2 plus appearing here, right? They are asking the weight percentage of Fe, the iron in this sample, right? Let's see how to solve this kind of question, right? So what they are asking is the weight percentage of Fe in the sample. This is what they are asking. Right? The asking data is all about iron, and what they have given is some data for the MnO4 minus. So MnO4 minus is the stuff which is given, right? Okay, just identify that thing, right? And then just think of the goal. Just think of the goal now. Weight percentage. Weight percentage is the one which we need to find here. Weight percentage. What that means? Weight percentage means you need to come up with the number of the weight of the interested substance, and then you have to divide it by the weight of the sample, the total weight of the sample. So total weight of the sample is given. Total weight of the sample is given in grams. Given in grams, right? So you need to come up with the weight of this thing as well as in grams, right? So the mass of this thing should be found in grams. So that is what the mass percentage means. No? Mass of the interested substance should be divided by mass of the sample. That is our goal, right? Goal and future. So if we are able to come up with the mass of the interested substance, we are done. You can divide the two and multiply with 100. Will give you the mass percentage. Right. So let's try to come up with grams here. What we need to do, Lavan? So this is the asking data and this is the given data. This is the given data. So use the given data to find out the mass of Fe2 plus. How to do that? So some data about MnO4 minus is given. So you can convert that data to number of moles of MnO4 minus. So this is the given, na? This is the asking, right? So you can convert the given data to moles of that species. So the concentration and the volume are given. So you can clearly convert that, the concentration and the volume, to number of moles of MnO4 minus. So after that, the two guys are with, right? So you have 5 here. The two guys are with 1 to 5 ratio. The two guys are with 1 to 5 ratio, right? So after finding number of moles of MnO4 minus, you can copy the number of moles of Fe2 plus, as those are with 1 to 5 mole ratio. If you know the number of Fe2 plus, the number of moles of Fe2 plus, you can copy the grams of Fe2 plus, right? By combining that number of moles with the G mole minus 1 value. Mole with the G mole minus 1 value will give you the grams ultimately, right? So that is the pathway of solving this problem. Let's solve the question step by step, right? Okay. Let's then come up with the given data. Let's try to find out its number of moles, right? So you can write here. So MnO4 minus moles, right? That is equal to 0.1 is the concentration, the mole dm minus 3 value for the MnO4 minus. If you multiply that thing with dm3 value, the dm3 will cancel off and the number will represent in moles, right? So you have a 20 cubic centimeters, so that is going to be 20 into 10 to the power minus 3, the dm cube value. Centimeter cubes could be converted to decimeter cubes by multiplying with 10 to the power minus 3. So that value is 2 into 10 to the power minus 3 number of moles. So this is the given species. So we can convert the number of moles of given species to bounded species, the asking species. So that is the Fe2 plus. So Fe2 plus moles. So that is going to be the 2 into 10 to the power minus 3 moles, which is the value of the MnO4 minus, is actually representing one portion. We need such 5 portions as Fe2 plus. We need such 5 portions, right? So this value is going to be 10 into 10 to the power minus 3 then. Right? As we know the number of moles, we can combine that thing with the g mole minus 1 of this thing to come up with the grams, right? So the Fe2 plus. Mass is then, right? You can multiply the number of moles with the g mole minus 1 value, no? So the mole thing will cancel off and answer will be given in terms of g. So the g mole minus 1 value for the Fe is 56. So the Fe's g mole minus 1 value is equal to the Fe2 plus, right? Because removing 2 electrons won't affect the mass of an atom, right? Removing 2 electrons won't affect the mass of an atom, right? So the Fe's molar weight is 56. So as the Fe2 plus, right? Multiply with 56. So the number is now 560 into 10 to the minus 3. So 0.56 grams. 0.56 grams. Right now? Then the weight percentage of Fe there. No worries, Lamaya. Fe's mass is equal to Fe2 plus mass, right? Both are equal, huh? Because removing 2 electrons won't affect, right? The mass, right? So weight percentage means the mass of the concerned substance, that is 0.56 grams, divided by the mass of the total sample, that is 2 grams, into 100. Percentage we are referring to. So it is going to be 28%. 28%. Right? No? That is your answer. Right? Just complete the stuff. Okay, Lamai. Let's try to solve this question. The question number 2, right? Appearing in page number 8, right? Let's try to solve this thing. So another question related to the mass percentage of sample. So this is what they are asking us, right? This is the asking thing, right? So the asking species is this thing. Right? Data are given. What? Right? The mass of precipitate is given. So in your equation, they have mentioned that barium sulfate as a solid, no? Barium sulfate as a solid. These are aqueous, right? These are mentioned as aqueous, while only the solid appearing. at your given equation is barium sulfate. So this is your precipitate. This is your precipitate. This is your precipitate as of the solid situation, right? So this is the given data. So this is the given data, right? So this is the asking data. So asking species, and this is the given species, right? So how to solve the stuff then? See, so you have a sample. You have a sample of 5 grams. They are right. There you have the what, ammonium sulfate and some non-reactive substance. Non-reactive substance. And the ammonium sulfate. Sorry, the ammonium sulfate, right? Right. So that is the question, right? Finally, they have got some 4.66 grams of precipitate, right? That is the given data, and asking is all about the ammonium sulfate's weight percentage, right? So for the ammonium sulfate weight percentage, this is the goal, right? For the ammonium sulfate weight percentage, first you need to come up with the weight of ammonium sulfate, mass of ammonium sulfate. So basically, mass of ammonium sulfate divided by the mass of sample into 100%, no, the weight percentage. So as the sample mass is given in grams, right, we need to find out the mass of this stuff also in grams. So unitless quantity, no, the mass percentage is a kind of unitless quantity, no, right? So if we are able to come up with the mass of ammonium sulfate in grams, then we can divide the two stuff, the mass of ammonium sulfate as well as the mass of sample. And if you are to multiply that thing with 100, that will give you the answer, right? So that is the idea, right? So come up with the mass of this thing. So this is the asking thing, asking species. We can use the given species, the data given species. So what we are supposed to do? First, convert this grams of the given species to its number of moles, to its number of moles. As the mole ratio is 1 to 1, as the mole ratio is 1 to 1, that number of moles will be equal to the number of moles of the asking species, ammonium sulfate. And as you know the number of moles of ammonium sulfate, you can compute the mass of ammonium sulfate with the use of G mole minus 1 data. The use of G mole minus 1 data. So G mole minus 1 data can be used to compute the mass. Right? No? Always you need to use the G mole minus 1 data to compute the mass, right? Okay, that's as simple as that, no? Right, let's do the stuff. So start with the given species, right? Data given species. So let's start with that. So to come up with the number of moles of that stuff, first we need to come up with the molar weight of this thing. G mole minus 1 value is needed to come up with the moles, right? So molar weight of barium sulfate. So barium is 137, sulfur is 32, 4 of oxygens means 16 into 4, right? The value is then 16 into 4, that is 64, 96 here, 96, and this one 233, no, 233. That is a G mole minus 1 value, right? With use of that, we can copy the moles of barium sulfate then. So the barium sulfate moles would be equal to that G value should be divided by G mole minus 1 value, right? then the G's will cancel off and you will come up with a number in terms of moles, right? So the G value is 4.66 should be divided by the G mole minus 1 value, which is 233, right? So actually this number is equal to what? 0.02, right? So now we can convert the barium sulfate moles to moles of the ammonium sulfate. So moles of ammonium sulfate. So 0.02 appears with the barium sulfate, right? That is for one portion. That is for one portion. We need such one portion as well. 1:1 ratio, right? So the same value, no? So moles of ammonium sulfate is also 0.02 moles. As we know the moles, we can copy the mass. As we know the moles, we can copy the mass. Right? We can copy the mass. That is what that is required to ultimately come up with the weight percentage, right? For that, to convert the moles to mass, first we need to come up with the molar weight of, or the G mole minus 1 value of ammonium sulfate. Let's come up with that. The ammonium sulfate G mole minus 1 value. So nitrogen is 14, hydrogen is 1 into 4 is 4, right? 4 into 14 is 18, 18 into 2 is 32, 18 into 2 plus the sulfate, 32 and 16 into 4. Here it is 64, 32 is 96, 96 into plus 96 plus 32. So 96 plus 36, that is 132, right? 132. Right? Then we can come up with the grams of ammonium sulfate with the use of that value as well as the number of moles. These two values will lead you to grams, right? So let's do that stuff. So the ammonium sulfate mass that is equal to, you need to multiply these two. You need to multiply these two to get rid of mole thing and come up with the G, right? So 0.02 moles should be multiplied by 132 G mole minus 1. So the value is going to be 264 with 2 decimals. So 2.64 grams. Right now? So we'll complete the question. So we need to come up with the percentage now. So I'll write it here. Right? So percentage. Or else I'll write it here, no worries, right? You can have the number in here as well, no? Right? Then I come to here for the percentage weight of ammonium sulfate. Right? What we do is divide the mass of the ammonium sulfate by the mass of the sample. Both should come up with the same units, right? So the mass of ammonium sulfate is 2.64 divided by mass of the sample, that is 5 grams. Have to divide by have to multiply by 100%, right? So that will give you the value as what? This is like, right? You are with 264 divided by 5, right? 264 divided by 5. So it is going to be 5, right? 14 is 2.8, no? So this is the answer, right? So it is 52.8. 52.8. That is your mass percentage of ammonium sulfate in this sample, right? So that is how we are supposed to come up with the answer, right? No? So complete the stuff. Right, no? This is how we are supposed to do a question regarding the mass percentages and mass fractions, right? Okay. So Lama, then we'll wind up at this stage, right? So we'll come up with the ppm concentration and stuff at the next class.